Alright, so we've been talking about energy conservation, but we also talked about how there are some situations where potential plus kinetic energy is not conserved. For example, when we had friction on the skate park, thermal energy contributed to our total mechanical energy, and we had this bulldog that was slowing down because his kinetic energy was turning into thermal energy due to friction on the track, and he eventually stopped. So what you're going to find out as we continue this unit over the next couple days, that there are situations where you can't use conservation of energy as in PE plus KE at the beginning equals PE plus KE at the end, because maybe some of the energy turned into sound, or maybe some of the energy turned into light, or some of the energy turned into heat. So sometimes in situations there are just more to consider than energy conservation takes into account. But physicists have discovered that there is a more fundamental thing in the universe that is always conserved, even if you have sound and heat and light happening out of a collision or out of a situation. And that more fundamental thing that you can just always trust as far as conservation goes is momentum. And so we're actually going to work a couple problems tonight using momentum conservation instead of energy conservation. And as we continue in this unit, I'll also be showing you when to know if you can use energy conservation or if you have to use momentum conservation. But let me just go ahead and say that when in doubt, momentum, always conserved. It's a fundamental thing in the universe that we're not quite sure about why it's so fundamental, but momentum is just always conserved. So let me zoom out this slide and then let's talk through this example. A child kicks a ball into a bucket. The ball and the bucket travel together after the collision. What is the final velocity of the ball and the bucket? Okay, there are some clear steps to solving this that if you follow them each time, just like energy conservation, it gets pretty easy. So we're going to have in every situation an initial momentum and a final momentum. And they will be the same. And then under each of those in the initial and final category, each object gets its own momentum. So just for now, let me color code this. Let's have the soccer ball be blue and the bucket be red. So each object gets its own momentum, m1, v1, I. So let's make the soccer ball object 1, plus, and if there were more than two objects, we'd do all of them, plus m2 v2 I equals m1 v1 f plus m2 v2 f. So the initial momentum of object 1 plus the initial momentum of object 2 equals the final momentum of object 1 plus the final momentum of object 2. And you should just write that. In fact, this part right here, anytime you realize a problem is momentum conservation, just write that. Without thinking, just write it down, and you're off to the right start. So I would even call this the don't think part. So don't think, just write the momentum at the beginning for each object and the momentum at the end of each object. Total momentum, just like total energy, conserved, except in the universe, no matter if there's heat or light or sound or energy becoming other things, the total momentum, definitely conserved, no matter what. Fact of the universe. Alright, so now that we've got that, we can eliminate things we don't need and continue solving the problem. So let's look at this situation. A child kicks a ball into the bucket. The ball and the bucket travel together after the collision. What's the final velocity of the ball in the bucket? So it looks like to me in this diagram we've got the mass of the ball, mass of the bucket, the initial velocity of the ball, so I'd call that v1i. And it looks like the bucket at the beginning is at rest, so v2i would be 0, making this term here 0. And they move off together, so they both have a final velocity, so nothing at the end goes away. But we can now rewrite this. M1 V1I equals M1 V1F plus M2 V2F. Now if two objects move together, and that won't always happen, but if two objects move together, their final velocities are the same. Because if they're moving together, they have to have the same velocity. They can't have different velocities. Just like two objects connected with a string had to have the same acceleration, if two objects move off together, they have the same velocity. So let's just call these both velocity f and factor them out. So now I've got m1 v1 I equals, and we're factoring out that vf because we decided it's the same for both objects, vf times m1 plus m2. Now, in this situation, I am trying to find the final velocity of the ball in the bucket. So vf is what I'm trying to find. So let's divide to get vf by itself, m1 plus m2, m1 plus m2. And now, just to make this pretty, move down here, I now have m1 v1I over m1 plus m2 equals, these parts canceled, vf. Okay, so now let's plug in the numbers. M1 is 0.40 kilograms. V1I, according to the diagram, is 8.5 meters per second. Over. Mass of the ball is 0.40 kilograms. The bucket is 0.15 kilograms. And now when I do out that math, I get that VF is 6.18 meters per second. And since this problem says final velocity, we need to give it a direction, so let's predict. It doesn't say magnitude, it asks me for the velocity. Bowling ball moved to the right. That means, or not bowling ball, the soccer ball moved to the right. That means the soccer ball's velocity was positive. And obviously when it hits that bucket, it's going to move to the right. So let's call that 6.18 meters per second to the right. Or if we had clearly defined to the right to be positive, we could just leave it as positive. But final velocity, it's moving to the right, and that's our number. Okay, any questions? Why don't you make a note and we can discuss them tomorrow.